Hey everybody, welcome into lecture number 27 of the semester. This is the penultimate lecture of the semester. There's only one left after this one. This lecture is on Turing machines, an introduction to Turing machines, and it covers the first part of section 13.5 of Rosen's book. So about the first half of this section. And the second half of this section will be covered in our last lecture of the semester, lecture 28. So let's begin this lecture by first stating a problem with the finite state automata that we've been studying up to this point in the last few lectures. The biggest problem here is that we cannot use our finite state automata as general models for computing machines. So finite state automata cannot be used as a general model. And just as one example here, as one example, let's consider the following set. So I'll say this is like example given, e.g. the set that consists of all the bit strings that have an even number of bits where the first n are zeros and the last n are ones. So this set 0 and 1, and this was an exercise earlier in the semester where your n is greater than or equal to 0. It was an exercise to show that this set is not regular. This is not regular, and it turns out that it cannot be recognized by finite state automata, but it is generally needed. Sets like this are you must be able to recognize these by computers, right? So let me say it this way, but computers must be able to recognize this. So they must be able to recognize this set. So the solution to this whole problem here is that we're going to study now a new type of machine called a Turing machine. So the solution is the Turing machine, and let's get right into this now with our definition of a Turing machine. And then we'll just do examples in this lecture, and in the next lecture we'll look into some more details about philosophy and theory of Turing machines. So like I said, let's start off with the definition here. A Turing machine, this is named after mathematician Alan Turing, the father of modern computing, you might say. But this is an ordered 4 tuple. It consists of S, I, F, S naught. So this should look familiar. It's a machine, right? Finite state machine, but it consists of the following. S is a finite set of states, so no surprise there. I here is an alphabet that always contains what we're going to call the blank symbol. So this is our alphabet of inputs, usually input alphabet, but it must contain the blank symbol, which we'll call B here as a placeholder. Sometimes you just don't even refer to this blank symbol. If you know you have a Turing machine, then B has always got to be a symbol in the alphabet. And then we have our transition function f. F is going to be a partial function. So how's this going to work? Well, f is going to, let me write it in 2 ways here. F is a partial function on this set S cross I. This is usual, right? And partial function just means that there are some inputs which may not have an output. So I'll write this in a minute. But the way f works is f is going to take in a state and an input, and it's going to give back a new state, a new input, and it's also going to give back what we're going to call a direction. And the direction set is just left and right, or right and left. Okay, so right and left are the 2 different directions. So it's going to be a transition function like the kind that we're used to, where it takes a state and an input, it gives back a new state and a new input, and it also gives back, though, a direction as well. All right, and of course S naught is our starting state. So this is our starting state. Now let's make a couple of notes before we look at our first example. Like I said, first of all, f being a partial function means that the domain of f is some subset of S cross I, but let me just write it this way. It's possible that some combinations of state and symbol do not have an output, all right? So it is possible that f of Sx is not defined for some pairs here that are made up of a state and then an input symbol. So, all right. The set, we'll call this maybe capital D, the set of L and R and L. This is called the directions set. It's the direction set. So that's part of the output. Our transition function is always going to output a direction. All right. And so when f is defined, what is it going to look like, right? So when f is defined on an input pair here, in this case a state and symbol pair, when f is defined in S comma X, the output, right? The output is an ordered triple that consists of a new state, a new symbol, we'll call it, but new input symbol, and then a direction, either L or R, but we'll represent that just by D for direction. And so a couple of things can be done here. Number one, we can write this in function notation. It is a transition function, even if it's just a partial function, it's still a function. So f of Sx equals this ordered triple now, S prime, X prime, and then D, the direction. But we could also think back to calculus where you could put the input and then comma the output and just combine these into one tuple. So the other way that we could write this is as a single 5 tuple where the inputs are the first two entries and then the last three entries are the ordered outputs. So this ordered 5 tuple kind of describes the transition, right? So it describes the transition function, at least for this given input. Now, what we can do is take the set of all of these 5 tuples determined by f. We'll write this as a definition, but the set of all 5 tuples, these are ordered, so ordered 5 tuples determined by this function f. This is called the set of, sometimes the set of is left out when you talk about it, but it's called the set of transition rules. Transition rules for the Turing machine. So our Turing machine we named T up here. If you look back up here, the Turing machine was named T. That's the set of the transition rules. Okay, so it turns out, and we'll see this as we move forward and do some examples very soon, that defining the set of transition rules is enough to define the Turing machine entirely, because when you define the transition rules, you're defining the set of states, right? The inputs and outputs together have to make up this set of finite states, and you're defining the input alphabet, right? The input alphabet is defined by the x and the x prime. Of course, D, the direction, is either L or R. Now, before we try to do some examples, we can look at kind of a schematic diagram here. And one of the most useful ways to think of a Turing machine is how it would operate on what the book calls a tape. So a tape representation. And so how does the Turing machine work here? Well, let me get my highlighter. We can define a couple things here. So the control unit is like, just, you can think of this if you're just schematically thinking of how you're going to build a Turing machine. It's like a box which switches between the states. So this is where the states switch. Now, at the same time, there is a tape that's kind of running through the control unit. So this tape right here, this has a whole bunch of symbols on it. And these symbols, the zeros, ones, and B's, remember B represents the blank symbol. 0, 1, and B here, these represent the elements of the input set I, the input alphabet I. So we've got our finite states up here. Notice this arrow's picking one of them out. We've got a tape which has written on it a bunch of symbols from the input alphabet. And so what does this do? Well, the machine is going to read the tape, right? So the control unit's going to read the tape, and it's going to take as its input, it's going to take the state that it's currently on in the control unit and it's going to take the input symbol from the tape. And remember what this outputs now. So the transition function takes in these two, right? Takes in these two entries. So in this case, it would be S2 and 0. And what's it going to output? Well, it's going to output a new state. So, well, I'll do an example in a second here, but it's going to input a new state. It's going to output a new state. It's going to output a new symbol, all right? So it's going to rewrite something on the tape. Right now it has read the tape. It has read the tape. It read the 0. It's going to write something, and then it's going to move in a direction. It's going to move the tape in a direction. So for example, if the output of our transition function at S2, state S2, and input 0 was to switch to state S4, write a 1, and go left, then what is this going to do? Well, it's going to do exactly what it sounds like, right? It's going to take the arrow, it's going to move it, and pick out S4, right? So it changes the state. It's going to rewrite. You know, it could write the same symbol. In other words, it could leave it alone. But in this example, it's going to write the new symbol, which is a 1, and then it's going to move left. So it's going to move left along the tape. So the tape kind of has to move right, but it's going to move left to the cell left of the tape, of the current one, right? So that's the L. The L there tells the control unit in some sense to move left. Probably if you built this, the tape would be moving, and the tape would move right in that setting. But the idea is that this cell right here, you move to the cell to the left, and then you repeat all this. So now the next input would be S4, 1 is the input, right? You would look at the output. Maybe it says to leave it as a 1, change the state to S3, move back to the right. Who knows, right? So you'd have to define all the different transition rules. But that's how a Turing machine works, and kind of like schematically, the idea of thinking of a tape running back and forth, maybe moving left and right, through the machine is a good way to interpret this. Okay, a couple more definitions here before we get to our examples. So I think, like I said, though, I think the image of the tape here is a good one to think about as you go through this. But a couple more, like I said, a couple more definitions. So it's possible, we said, that our function is just a partial function, right? So if f of sx is not defined, remember, it doesn't have to be in the domain, right? So if it's not defined, then we say that the machine will halt. The Turing machine will halt. So will halt. And so we're defining the halt there. And we're going to use the act of the machine halting to help us use these machines to model some different situations as we move forward. I already said a common way to define our Turing machine is just to define the set of transition rules, and that is enough, it turns out. And the final thing that we should say here is that at the beginning of an operation, at the beginning of operating a Turing machine, we make some assumptions here, especially if we're thinking of the tape. So this is in reference to the tape. But at the beginning of operation, a Turing machine, so I'll just call it T machine, is assumed to be in its start state. So to be in its start state, that's S0, right? Or starting state, you might want to say in this context, but starting state S0, and over the leftmost non-blank tape symbol. All right, so this reminds me that I forgot to say something very important. It's written here, but I didn't point it out. The tape is infinite in both directions in this model, but only finitely many of them are non-blank. Only finitely many of the entries can be non-blank at any time. All right, so there is then a leftmost non-blank symbol. That doesn't mean that the machine can't go left, right? It can still go left, but it'll end up on blanks if it moves left. So the leftmost non-blank symbol. Now the idea of having the tape, be infinite in both directions is so that the tape will continue to run even if you've gone left of the leftmost or right of the rightmost. You can just continue to run it, and your machine can take as one of its input symbols, it can take the B, right? It can take the blank symbol as one of its input symbols. Remember, that was part of the definition up here, right? So okay, well, this is theoretical. We've drawn a tape, or at least we've taken a picture from the book and highlighted a Turing tape machine here in some sense. And now we would like to do some examples. So item number 2 of our lecture here. Let's look at an example where the machine is defined by the set of transition rules to start with. Okay, so here's an example. So let's consider the Turing machine defined as follows. Now, what we have to do is list all of the ordered 5 tuples. In the book, they tend to just list the tuples, but I like to make a table, okay? So I'm going to make a table which it's represented like this. So it represents our transition function. S and X are the inputs, S prime, X prime, and D are the outputs. So this is exactly what we've done before, but then I just make a column for each. So S, X, S prime, X prime, D. And then I just list off. So each row of this table will represent one of the 5 tuples. So here's what we've got. I'll just write out the examples here, and then we can go through and look at how this works. But here's S0, 0, S0, 0, and then R. So this says that when the state is the starting state, S0, and the input is 0, you don't change anything, right? It remains S0, remains 0, but it does shift the tape to the right. Okay, so there is part of the output there. And then if S0, if the input is 1, then the output is changes the state to S1. It writes the output 1, right? Or writes the symbol 1 and then moves to the right. If the other option is that the input could be a B, the symbol could be a B in the initial state S0. In this case, it switches to state 3, S3, writes B, right? Keeps it blank, I should say, and then moves to the right, but it switches the state. There's a couple more here. So then S1, so there's 3 possibilities of inputs for S1. Remember, it's a partial function, so you don't have to define everything, right? But S2, we're only going to define one thing. So when its state is S1 and the symbol is 0, then this is going to change the state to S0, write a 0, or keep it as a 0, and move the tape right. If the state is S1 and the input symbol is 1, it's going to change the state to S2, rewrite that as a 0, and move to the left. Okay, so it's going to write over the 1 as a 0. If it's blank, then it's going to change the state to S3, leave it blank, and move to the right. And then finally, S2, if the input is 1, then S3, it gives back S3, 0, and R. Okay, so the idea here is we want to see how this thing is going to run. If we start at the initial state and we put a tape in here, I did not write down exactly which, whoops, oh, that's not what I meant to do. Sorry. So I have a picture here. So the idea is to run this on the initial state. So here's an image of how this works. All right, so I'll try to get this so we can see, kind of see a little bit of what's going on. Here, I'll move the table in a second here. So this is how, this is our transition rules, right? So let's move this over here so we can get everything on the same page. And take a look at how this is going to work. All right, so the idea here is that we start with S0, 0. So S0 is the initial position. The initial symbol is 0. We plug these into our transition function. What does it tell us to do? So by the way, I guess the part of the problem that I didn't write down is we want to put a tape in here into our machine. So this defines our machine. But we can put a tape into our machine with any kind of symbols written on it, right? So this example right here is plugging in the tape into our machine whose symbols are 0, 1, 0, 1, 1, 0. Okay? So we're plugging in. This is really the idea of the example. So sorry, I missed that, right? But we're going to plug in the string. So the string 0, 1, 0, 1, 1, 0 to the machine, right? Plug this string into the machine T. And so this is our example here. So how's it going to work? Well, it works one thing at a time. And notice that the tape has these blank spots on the outside, so that if we go off the tape, it's fine, right? We can still run the output, right? We can run the Turing machine on it. So we run the tape through. It starts at S0 always, initial state, and the input is 0. Right? The input is 0 because of this extra part of the example here. So now we do exactly what it says, which is to leave that as S0, leave the state as S0, leave that as a 0, and move to the right. So move to the right is the key, right? So the next thing is now it's an S0 still, but it's a 1 as an input. So S0 and 1 changes the state to S1, but it leaves the symbol as a 1. So it writes a 1, and then it moves to the right. So leave it as a 1. Move to the right. Now you've got S1 with a 0 as the input. So S1, 0, what's it going to do? It's going to change the state back to S0 and leave that as a 0, right? And move to the right yet again. Next, what's it going to do? Now you're at S0. So S0 is the state. It's got a 1 as the next term in the tape, right? So S0 and 1 says to change the state to S1 and move one unit to the right, right? Move to the right. So now we're over here. Now we're at S1, 1. So now we're going to finally get to change something, right? So this one, so S1 and 1 is the input, says to change the state to S2 and overwrite, okay? And overwrite. So at this one, we're going to overwrite this, right, as a 0. So the machine is doing this. The machine is doing this, and then it goes not to the right, but now this time it goes to the left, right? So it goes back to the left, and by the way, it changed the state to S2. So now the state is S2 and 1. S2 and 1 says change the state to S3 and output a 0, right? Change the state to S3 and output overwrite that as a 0. So a couple things. Changes the state to S3. It's going to write this as a 0, right? So it's doing this. If you look at what the pictures are doing, it's doing this. And at this point, the input, right, the tape, what is it? The machine is reading a state of S3 and an input of 0. S3, 0 is not a combination that's defined by our transition rules, right? So there's no transition, there's no rule for the input S3, comma 0. And so the machine stops, it halts, right? And so now you look at the tape. You look at the tape, and what do you have? So the tape reads, after all this, right, the tape reads 0, 1, 0, 0, 0, 0. So it overwrote the two ones as zeros there, and then it stopped. It just stopped working, and so at the end of all that, that's it. That's the output, right? So if you were to imagine this working on an actual tape, the tape would go right, left, little, right, left, a little bit of rewriting, maybe some noise that it makes to rewrite over the tape, and then at the end it would just stop, right? It would just stop, you pull out the tape, and here's what you would see. All right, so there's an example of a Turing machine. Okay, so on to the next thing then. We have looked at it, we've written the definition, we've looked at an example, seen some nice pictures that I think will help us. So the next idea is we want to use a Turing machine to recognize a set. So especially if we're going to try to do any kind of language recognition or something, it's not going to be language recognition necessarily, but we definitely need to use these machines to recognize sets. It's kind of one of the computing ideas here, right? So using Turing machines to recognize sets. All right, before we can recognize sets, we have to define what we mean by a final state for a Turing machine. So I'll just write this out here, but a final state of I'm just going to write a T machine again, a Turing machine. This is a state that is not in any in the first position of any 5 tuples in the in the transition rules. Okay, so it's a state that is not in the first position in the 5 tuples, in any 5 tuples. In any 5 tuple of the transition rules. All right, so if we go back up to our previous example, there's one final state here, right? There's a final state that we can see pretty clearly. If we look at the states that are in the first entry, we see S0, S1, S2, but we do not see S3, right? So this is a final state. So can't read that, but so yeah. But this is our S3 is the final state, the only final state for this example here. There's another S3 up here, right? Okay, so, but anyway, we can define final states just based on the transition rules. So it's any state that's in the state set, but is not in the leftmost or the firstmost position of the 5 tuple. And now we can define what we mean by recognition of a set. So here's our definition. Let's suppose V is a subset of the alphabet I. So let's let V be a subset of the alphabet I. I'm just going to use symbols here. We then say a Turing machine T, which is of course equal to, whoops-a-daisy, the state set S, I, F, and then S naught. This we say recognizes a string, so recognizes a string X in V star. So remember, V star is a set of all strings made up of the elements of V, but it recognizes a string V X in V star if and only if T, starting in the initial position when thinking of writing on tape, so T starting in the initial position when X is written on tape, halts in a final state. So two things are happening here, right? The Turing machine has to halt after X's input. So it halts at some point after X's input. And not only does it halt, but it halts in a final state. So we can add to this, right? So T is said to recognize an entire subset of V star if and only if it recognizes every X that's in that subset. So let me write it out. But T is said to recognize a subset A of V star if and only if X is recognized by T. So this is worded a little bit differently in the book. It just says if here. But if F is recognized by T, if and only if X is in A. So X is recognized by T if and only if X is in A. So what does this mean then? So as a note here, we'll write to recognize this subset A in V star, we cannot use symbols that are not in V. Right? We cannot use symbols that are not in V. All right? So this is pretty important, and we'll see this later on, maybe in the next lecture especially, as we look through more examples of these Turing machines. But the following here, so a Turing machine is another definition. This will be very useful. But a Turing machine fails. Whoops. Oh, this is sorry. getting ahead of myself. This is not a definition, but it fails to recognize a string in two different cases, right? There's two ways that it can fail to recognize a string. So let's write down what they are. But it fails to recognize some x in v star if either, number one, it never halts, right? So it never halts. Or the other possibility is that it halts, but it's not in a final state. So it halts in a state that is not final. So these are the two possibilities of how you can fail, how a machine can fail to recognize a string from a given subset of the language v star, or the set of strings v star. All right, well, let's look at another example here. A couple more. We've got a couple examples. So here's two examples. We'll start with one, obviously. The first one, we want to try to find a machine that recognizes the set of bit strings that have a 1 as their second bit. So find a Turing machine that recognizes all of the bit strings with a 1 as the second bit, and this is the second bit from left to right. So in other words, we want to, this turns out to be a regular set, so but it turns out that the set in regular notation, so this is the regular set that looks like this. So it's either 0 or 1, so that's 0 union 1, right? Then it's a 1, and then it's 0 union 1 star, right? So it's something, 1, and then a whole bunch of others. It doesn't matter what else, right? So something, 1, else, doesn't matter. So let's do it, okay? So we're going to do this by defining the transition rules, right? So we'll define the transition rules here. And again, I'm going to do this in kind of the table method, and then I'll justify each transition rule that I add, at least by saying it out loud, but you should check all of these, okay? So we're going to define our machine as follows. So here, again, I'm going to make a table. So S, X, S prime, X prime, and then D. So we're going to build this machine pretty simple-minded. We're going to put in, again, if we think of this as taking in a tape, we're going to put the tape in, and the machine's just going to move from left to right. It's just going to read the bits of the bit string, and it's going to halt in a final state if it's correct, right? So if it goes something and then 1, and then it doesn't matter what else, or it's going to halt in a non-final state otherwise, right? Or it's just going to keep, I guess you could make it so it just doesn't halt, it just keeps on going. So here's how we're going to do it for this one, though. So we need to read the first state, basically, right? We need to read the first bit, sorry, and then we're going to change it to a new state, okay? So it's going to take the first state, the starting state, and it's going to read the first bit. It's going to change the state from S0 to S1, but it's going to keep that bit the same, right? And just move to the right. So this just tells you that everything has started. It starts in state S0 and moves to state S1, but it doesn't change anything. So same thing if the first entry is a 1, right? The first symbol is a 1. Change it to state S1. You leave this as a 1. Don't change anything. Move to the next bit. Now the next bit is where the most important thing happens, because the second bit is the one that we care the most about, right? So the second bit is going to be the one that we have to look at and see, is it a 1 or is it something else, right? Is it a 1 or is it something else? So in this one, we're already in state 1, S1. So this is just to indicate that we're on the second bit, this state right here, right? So we've moved to the second bit. That's why the state is S1. From here, we need to read it, right? So from the state S1, if the initial, if it's written as a 0, then we're going to return a different state, S2, and leave it the same. Again, the goal of this machine is not to write anything. It's just to read everything and recognize whether or not what it's read is what we want or not. So it changes to state S2 if the second bit is not what we want, if it's a 0. And it's going to change the second bit, so it's going to read the second bit, and if it's S1, it's going to change the state to S3 if it is what we want, right? So we can, again, it doesn't matter what we'll leave it the same. Just let it write out a 1. So what we want to do is we want to then we want to recognize, what I should say, is we want to recognize the states, the strings that are input that change to state 3 here, right? And we want to ignore the rest of them, right? So we want to ignore the ones that change to state 2. So this means that S3 should be a final state, right? So we want to have this be a final state, and we want this thing to halt on the final state S3. So what we need to do then is include something for S2 on the left-hand side to make it so that it's not a final state. That's the goal here. We want to make sure that this S2 is not a final state. We don't want the machine to halt in this final state of S2. So we just need something, right? So S2, notice that the S2 in 0 is the output here, right? So just have it stay the same, right? S2, 0, R. Just move to the right. So there you go. So S2, 0, R. So that just gives us a transition rule for S2, meaning that S2 is not a final state now, right? So what this will do is it'll make sure that S3 is the final state when the machine, halts here. Because once you get to S3, there's no rules for S3, so it's going to stop, right? It will halt, and it's in a final state. So the machine, we also want to make sure that when it reads the bits that it takes care of the bits that either the blank bit, right, or the blank string, or the string that just has one entry and nothing else. So those two should not be recognized by this, right? So what we have to do is make sure that it switches both of those into state S2. And so how do we do that? Well, the empty string is the one that starts in, from the starting position. The first entry is B, it's blank, right? It's a blank string. We'll switch to state S2, 0R. So that's not a final state. And then the other option is that from S1, it could be blank, right? So from the second position, it could just be 0 or 1. Those can't have a 1 in the second bit because they don't have a second bit. So we need to take care of those as well, right? So S1, if that's blank, we switch that to S2, 0 as well, and move to the right. So as a recommended exercise, make sure that this machine terminates in a final state only if the second bit is a 1. So we can kind of see that, right? The only one that switches to a final state at all is this one, S3. Okay, so that's it. There's a machine that recognizes all the strings that have a second bit, all the strings of bit, the bit strings that have a second bit entry as a 1. All right, let's look at another example. So this one, let's go back to our original way back up here. We said that one of the problems is that a finite state automata or automaton could not recognize this set right here, right? Equal number of zeros and ones. All the first n of them are zeros, the last n are all ones. So let's try to find a Turing machine that recognizes this. In this case, we'll do this for, so we'll do this for the case when it's not the empty string, so that's at least 0, 1, and maybe, and then larger. But find a T machine that recognizes this set, 0n, 1n. Again, for n bigger than or equal to 1. All right, so the first thing that we're going to do is we're going to use an auxiliary symbol here. And so this is going to be called a marker. But here's the solution for this one. And I'll leave part of this as a recommended exercise here. But for this one, we'll use, like I said, an auxiliary symbol. We'll call it M. M for marker. Symbol M as a marker. So this is an extra symbol in I that is not in V. I mean, extra might not be the right word, but it's a symbol in I in the alphabet that is not in the set V of stuff that we're going to try to read, right? The strings that we want to read. Recognize. So in this case, our set V is obviously going to be just 0 and 1, because especially since we're starting with n greater than or equal to 1 here, all of our bit strings that we want to recognize are just combinations of zeros and ones, but our alphabet is going to be 0, 1, M, B is always in there, so we don't have to write it. And basically, this one gets a little bit complicated. So I'm going to write out the table here. But the basic idea is that suppose, and so this is what you're going to want to check as a recommended exercise, but suppose that you are given a string, say 1, 1, 1, 0, 0, 0, like this. That wouldn't be right because it's supposed to be zeros on the left and ones on the right. So I've got it backwards. Sorry. So 0, 0, 0, 0, 1, 1, 1, 1. We'll add an extra one. Okay, we want to plug this into our machine, and we want to recognize whether or not this starts with, say, n zeros and ends with n ones. So what it's going to do is it's going to start here, obviously, right? And it's going to rewrite this as an M, and then it's going to move to the right all the way over until it gets over to this symbol, okay? So to this symbol, and then it's going to write this one as an M as long as it's a 1, and then it's going to go back over here, all the way here. It's going to read this one, make sure this is a 0, and if it is, it's going to make it an M, and then it's going to go back over here and read this symbol, and as long as this one's a 1, that's going to be an M. So it's going to switch back and forth, right? It's going to start with 0, it's going to move to the right and make sure the rightmost symbol. So if the next one's a B, right? So how's it going to do it, right? Remember, we have this strip actually that's infinite. So blank, blank, etc., blank, blank, etc. Right? So once it gets over here and sees a B, it's going to just go back and then read this one. So then it'll know that this is the rightmost bit, right? So again, start here with the leftmost 0, rewrite it as an M. M here as just means marker. That just means that it's already been viewed or seen, or what, you know, however you want to say it, but it's already been observed, right? So marked, it's been marked that it's correct. Then you move to the right, you see a B, that means you're at the rightmost edge, right? So you go back to the previous one. If that's a 1, you check and see if it's a 1. If it's a 1, you mark it. Then you go back to the left, right, until you see this M. That means you've already marked the previous one to the left, so you go back to the next one, right? It's an M. It's a 0. It's correct. It's what it's supposed to be. You mark it. You go back to the right. You notice there's an M. You go back to the previous one. So how's it going to work? This thing's going to go, it's going to mark this one, go over, 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 1 too far, go back, check it, over, 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 1 too far, go back, check it, etc., right? So you can kind of envision this. It just sweeps back and forth. It's not the most complicated thing. But actually the machine, the transition rules are a bit complicated. So it turns out we need 6 states, and only one of them will be a final state. So here's the I'll call it the transition rule table. But this is a Turing machine that's going to check to see if we have these symmetric bit strings of zeros and ones. So again, here's our S, here's our X, here's our S prime. X prime, here's our direction. And as I write these down, as we just talked about how this machine is going to work, think about which one, what is each one of them doing, right? So from the start state, S naught, we check, is this 0, right? Change it to S1, mark it, move to the right. All right, so then S1, you've moved to the right. So S1, 0, S1, 0, move to the right. Remember, there's supposed to be zeros in this area here, right? So it's supposed to be zeros until you get to this one. So if this is a 1, then what do you have to do? You stay in state S1, because this state S1 is just moving from left to right. That's the whole idea. State S1 is just telling you, go to the right. If it's a 1, well, you change your X prime to a 1 here, and you just keep on moving. In other words, you're not rewriting anything. You're not rewriting anything here. You're just moving over. And what are you looking for? You're looking for either a B or an M on the right-hand side. So if this is if S1, if we see, let's just work from down here, from up here. If you see a B, then you have to go back to the left, right? You leave it alone and you go back to the left. So if S1 sees a B, then you leave it as a B, but you go back to the left. Sorry, you need to change the state, right? You have to tell the machine that you've reached the right edge. So you change to state S2, but you leave it as a B and you move back to the left, and now you're looking at the previous one, right? After you've done this once, it won't be a B anymore that is your indicator. It's going to be an M, right? So you also need the same thing here that switches to S2 when it sees an M and goes back to the left. All right, so at this point, S2 needs to check, is it a 1 or is it not, right? So is it a 1 or is it not a 1? So now S2, you're going to say, okay, we're in state S2. It better be a 1. And if it is, S3 would just change the state to S3. We mark it, and we keep moving to the left, right? So you check to see, is it a 1? You mark it. You keep moving back to the left. If it's a 0, the machine is going to halt, and it's not going to be in a final state because S2 automatically now is not in a final state, right? So S2, 0 is not included as a transition rule from this left-hand side here. And this S2 is clearly not a final state because there's somewhere else it could have gone. So there we go. So that would tell us that it has not been recognized, right? So, but if we wanted to keep going, what do we have to do next? Well, now we have to go back to the left until we reach an M. We don't have to worry about hitting a B as we go to the left, but we have to go back until we reach an M, right? So as we go along, if it's a 1, S3 is a 1, we leave it alone, move to the left. We kind of repeat the whole process, right? So now we're in state S3. We see a 1, we leave it alone, we move to the left, right? As we move along to the left, S3, when we see a 0, that's okay too. We leave it alone. So S3, if we see a 0, so here we're actually going to switch this state then to S4 and leave it alone, but keep moving to the left because now we want to make sure that we are in the, yeah, so we just want to make sure that we are identifying that we're supposed to be seeing zeros here. If we get to S3 and we see an M, that means we've reached the left edge. We've reached the marker before, right? From state 3, we've reached the marker before we've gotten to any zeros because we changed to state 4 here, if it had, right? So then we're going to change that to state 5. Leave it marked, and then just move back to the right. And now we kind of get to the good stuff here. So from state S4, if we see a 0, we're okay with that. Just keep on moving to the left, because remember, that just means that we've switched from 1s to 0s. And now there's two possibilities. From state 4, we could see an M, in which case we just want to mark it and repeat the whole process, right? So from this state 4, if we see an M, after going to the left of these zeros, we find an M, we mark it, and we repeat the whole process. Go back to S0. S0, we leave it marked, obviously, and move to the right. Okay? From S5, so remember S5 is what? We found a marker before we saw a 0. So from S5, we need to look at the previous one to the right. We mark this as S6. We mark it, and we're done. So actually, yeah, we would mark all of these, right? So if we mark this from S3 to S5, that means that S3, we just found a 1. We marked it with an M. We moved to the left. There's an M there. Everything's done. So that means everything's done, and this is the only final state now. So this is the only final state, S6. Okay, so as this thing runs, it goes back and forth, back and forth, back and forth. And for most of its going back and forth, it's not doing much, right? So it starts here at this left endpoint. It marks it, starts by marking it. And then it takes, in this case, with this example, it would take 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9 steps where it didn't do anything, right? It didn't mark anything. Or I guess at least 8 steps where it didn't mark anything until it marks something again. And then it's going to go back and it's going to be less and less each time, but there's going to be a whole bunch of steps where you don't mark anything there, right? But essentially what it would do is it would take this thing with a lot of steps. It would start by marking here, right? And then it would mark, the next one would look like this, right? But that's a lot of steps in there. So lots of steps in between there. And then same thing, right? As it goes back, the next one will be M, M, 0, 0, 1, 1, 1, M. Again, lots of steps in there, right? Eventually, this thing, because it is 4 zeros followed by 4 ones, would end in all M's. The final state would be S6. It would be recognized by this machine. Okay, so as a recommended exercise, just make sure that you verify that this works. I think we talked through most of it. But verify that this works. And we've got one more thing that we want to look at here. And this is how we can use Turing machines to compute functions. All right. And like I said, this is only half of this section, but about half of this section. I wanted to go into this in a lot of detail. So we'll pick up from here in the next lecture after we're done with this, but computing functions with Turing machines. So the idea here is that a Turing machine can be thought of as a computer or something that, does, well, it says in the book, he says that it can be thought of as a computer that finds the value of partial functions. And the idea here is, how does it do that, right? So let's suppose that suppose a Turing machine, given an input x, halts on the string y. So input string here. So what I mean is, given a tape with the input string written on it as an x. So given an input string x halts on the string y. On its tape. So you input the tape with the string x written, the Turing machine does something, goes back and forth, it finally halts, you pull the tape out, and on the tape you have a new string, y. Then you can define this as t of x equals y, right? So you input the tape with x written on it, Turing machine did something, it output y. That's exactly what a function does, right? So, or at least a partial function, it's at least a partial function, right? Because it might not stop, it might not halt at all, but, we can fix that by doing the following here. So the domain of t, we can define the domain to just be the set of all strings for which t halts, right? So it's a set of all strings for which t eventually halts. And then t of x is just thought to be undefined if it does not halt. So just like, now it's a function, right? So just like regular functions. So you input x, nothing, it doesn't halt, then, it's no output. All right, let's write down then some more conventions here, and then we'll finish with an example. But we want to be able to represent integers on tape, okay? So the question becomes, how can we represent integers on tape? So we're going to have to be able to do this if we want to use our machines to compute things with integers. But to represent a non-negative integer, so this is a positive plus 0, right? Integer on a tape. we can use what are called unary operations. And we'll see an example. We're actually going to represent tuples of non-negative integers, but let's start with just the non-negative integers to start with. The non-negative integer 1, or n, sorry, can be represented by, so on tape, can be represented by a string of n plus 1 ones. So for example, so by the way, so this is fine. So by example, our 0 can be represented by just a 1. 5 would be represented by 1, 1, 1, 1, 1, 1, so 6 ones. And then obviously, I won't write this out, but I'll write it. 21 can be represented by 22 ones, right? So there you go. That should be 22 ones. Not as fancy looking, but 22 ones. So that's how you can represent integers on your tape. Now the question is, if we're going to try to represent a function, our functions, remember our transition function takes in tuples, right? So it takes in tuples, but let's say it this way. A k tuple of non-negative integers can be represented by the integers separated by asterisks. So for example, when there's a comma, so if we want to represent 2, 1, 0, 3, well, how's this going to be represented? So 2, that's 1, 1, 1. So there's a number 2, comma, asterisk. Okay, so we're going to add a symbol to our set of inputs that the machine can read, which is just an asterisk. All right, and then 1, well, that's a 1, 1. Star 0, that's 1. Star 3, it's 4 of those, right? So the machine would read this as 1, 2, 3, 2, right? So we read this as 2, comma, 1, comma, 0, comma, 3, right? And so that's exactly what it would do. So now the question is, how can we use this idea to actually build a machine that does something for us? So let's try one of the simplest possibilities, which is just add 2 non-negative integers. All right, so this is our example here. We want to build a machine. So we want to build a machine that adds 2 non-negative integers. Kind of as basic as it can get, right? So the idea here is that the function that we want to model or work with is it takes in 2 non-negative integers and it spits out their sum, right? So how is this going to work? Well, let's just draw this out, right? Let's do an example. So we want to add f of 3 and 4 should be 7, right? Well, what's it going to take in? It's going to take in 3 comma 4. So that's 4 ones, a star, 1, 2, 3, 4, 5 ones, right? But it should spit out after that. So the function should operate on this, the Turing machine, I should say. Turing machine is going to represent this function. The Turing machine should take this in, and it should give us back just a list of just 8 ones. Well, look at this. If we count these, what do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 ones over here, and we have a star. So essentially what we have to do is delete one of these ones and delete the star, right? Delete the 1 and the asterisk. So that's the idea. So let's see how we can do it. So goal, this is our goal, right? Delete the leading one and the asterisk. So here are the rules, and I'll let you guys verify it, but here are our rules. So S, X, S prime, X prime, D. All right, first of all, S naught, it's going to take in a 1, right? Unless that's a 0. If that's a 0 there, then it's always going to be a 1, right? Because even 0 is represented by a 1. So it's going to take in a 1. This is the only start state that we need to worry about. It's going to change this to a blank. Okay, it's just going to blank it out. That's how you delete it. And then move to the right. So it changes the state to S1, and it changes the symbol from a 1 to a blank. So there we've deleted the 1, the extra 1. The extra 1 is gone, right? Now, from state S1, there are a couple possibilities. It could either be a star. So this is if your number was 0, right? It could be a star. In this case, you switch to state S3. By the way, S3 is going to be a final state. You blank this one out, move to the right, you're done, right? It's over, you're done. So because S3 is going to be a final state, so the machine will halt. So in that case, if you add, 0 plus 3 should equal 3, right? So it's 1 star 1 2 3 4 becomes 1 2 3 4. So what does this machine do? It just blanks both of those, right? Blanks both of those. All right, well, what if it's not? What if that's not the case? What if it's more like this? Well, then the possibility is that S1 is going to, after your first step, you're going to see a 1, right? So in that case, then it's going to change the state to S2, and it's going to blank that out. All right, so you change it to state S2, you blank it out. So now what do we have? After this many steps, we had, let me write out what the machine has done so far. To this one, right, to our 3 plus 4. So the first step was to blank out the first one, 1 1 1 star 1 1 1 1 1, right? The next step is it sees a 1 here. If it had seen a star, we'd be done, right? Just by the previous one. Now we're dealing with the case where it doesn't see that. So it still blanks it out, right? So now we've got blank blank 1 1 star 1 2 3 4 5. Now the question is, so now you can see what's going to happen, right? It's going to have to rewrite. Now it's going to be looking for an asterisk, and it's going to try to rewrite that as a 1. So that's going to be the next thing, right? All right, so now we're in state S2, right? So now from S2, we continue on. So now from S2, either we see a 1, so the next would be a 1, right? What do we do then? We leave it alone. Leave yourself in state S2, leave this as a 1, move to the next symbol. Still a 1. Does the same thing. Next symbol. Now it's going to see the asterisk, right? So now if you're in state S2, you see the asterisk. You turn it to the final state, S3, but you rewrite this as a 1 before you move along. Okay, so this is the machine. So at this point, it's going to become BB 1 1 1 1 1 1 1 1. And then, of course, you ignore the blanks, right? A blank just basically means erase. But keeping track of the states is the way that this takes care of, okay, change to state 1, you've done it once, and then you're either looking for asterisk or you go to the next one, right? Change the state and then look for asterisk again. All right, well, that's how this works. Again, recommended exercise. Make sure you really, truly understand this, verify this, that this is really working. And we'll leave this here, and I'll see you guys in the next lecture, which will be the last lecture of the semester.